Welcome to Podcast Learnin' Fun. Let's start today's journey of learning. So imagine you're trying to describe the exact moment a basketball hits the ground.
Okay.
You know, that instantaneous burst of sound and energy.
Yeah.
It's a real world example of something that the Dirac delta function helps us model.
Right.
But it's not your typical function.
No.
Think of it more as a powerful concept that physicists and engineers use to represent something that's happening in a single infinitesimally small point in time or space.
It's a fascinating concept, really. One of the most important properties is its ability to sift through information.
Okay.
Kind of like a search function that zeroes in on a very specific value within a continuous function.
Interesting.
This sifting property is used everywhere, from image processing, where it can detect edges, to communication systems, where it helps isolate specific signals.
So it's like being able to find a needle in a haystack, but instead of searching through hay, we're sifting through complex mathematical data.
Exactly.
That's a pretty powerful tool.
It is.
But what about this concept of the delta function being normalized? What does that even mean?
Normalization essentially means that even though the delta function represents an infinite spike at a single point, the total area under its curve is always 1. It's like we're saying, yes, this event is incredibly powerful, but we can still quantify it and make it work within our mathematical framework.
Right.
This normalization ensures consistency and predictability in our models.
Okay.
Another important thing to remember is that the delta function has what we call support.
Okay.
This refers to the region where a function is non-zero. The delta function is 0 everywhere except at its single point of action where it becomes infinitely large.
So if I'm picturing this correctly, it's like a flat line with a sudden, infinitely tall spike at one specific point.
Yes.
That's a pretty unique characteristic for sure. It makes sense that it's used to model those instantaneous events, those boosts of energy in a short time span. But how does it relate to exponential functions? I remember reading something about that.
You're right. The delta function can actually be expressed as an infinite sum of exponential functions.
Okay.
It's similar to how a single note on a piano can be broken down into many different frequencies called harmonics. The delta function does something similar with waves, combining them in a way that creates a focused, instantaneous effect.
So we're talking about breaking down a complex wave into its simplest parts, kind of like analyzing a musical chord to figure out the individual notes that make it up.
Exactly. And this leads us to the concept of the Fourier transform, a powerful tool that helps us break down complex signals into their individual frequency components. It's like taking apart a smoothie and separating it back into its individual fruits and vegetables.
And the delta function acts like a filter in this process, picking out the specific frequencies we're interested in. It's amazing how such a seemingly simple concept can have such broad applications.
Absolutely. It helps us isolate and understand the fundamental components of complex signals, making it invaluable across many fields. And what's even more fascinating is the role the delta function plays in the world of quantum mechanics, where it helps us model these point interactions between particles. For example, imagine trying to understand the interaction between an electron and a tiny localized particle. The delta function helps us model this interaction as a sudden localized event.
So it's like saying, here's an electron minding its own business, and bam, it gets hit with a tiny concentrated burst of energy.
Exactly. It provides a powerful way to describe these fundamental interactions in the quantum world. It really highlights the power of this seemingly simple mathematical tool to help us understand these mind-boggling quantum phenomena. Now, to give you a more concrete example of how this all works,
Okay.
let's talk about a specific scenario in quantum mechanics where the delta function proves particularly useful, the concept of a potential well.
A potential well. That sounds a bit like a trap for tiny particles.
It's a great analogy. Imagine you have a tiny particle, like an electron, confined within a narrow region of space. This confined region is what we call a potential well. And the delta function potential represents a very specific type of well. It's infinitely deep and narrow, acting like a sharp spike at a single point.
Okay, so it's like an incredibly concentrated well that only exists at one specific location. But how does that help us understand anything about how particles behave?
Well, while it might seem like an oversimplification, it's surprisingly useful for modeling certain physical systems. We incorporate it into the Schrödinger equation, which is the fundamental equation that governs the behavior of quantum particles.
Ah, yes, the Schrödinger equation. I've heard it's notoriously complex and mysterious.
It can be, but the beauty of using the delta function is that it simplifies things. By representing the potential well as a delta function, we can solve the Schrödinger equation and get a clear picture of how the electron behaves within that well.
So it's like a mathematical shortcut that allows us to make sense of this complex quantum world without getting bogged down in the intricacies of the equations.
Exactly. And the solutions we get are quite interesting. They show us that the electron is mostly confined within the well, but there's also a small probability of it tunneling through the potential barrier.
Tunneling, like it's digging its way out of the well.
Precisely. Quantum tunneling is one of those mind-boggling phenomena in the quantum world. It means that even if a particle doesn't have enough energy to overcome a barrier, there's still a chance it can pass right through it.
That's incredible. It seems counterintuitive, but I guess that's the nature of the quantum world. So the delta function not only helps us model the well itself, but also reveals these amazing quantum effects. I'm starting to understand how powerful this concept really is.
And it doesn't stop there.
Mhm.
Remember when we talked about the Fourier transform? It turns out that the Fourier transform of a delta function in position space actually gives us a delta function in momentum space.
Hold on, let me wrap my head around that. Are we saying that we're going from a sharp spike representing the particle's position to a sharp spike representing its momentum?
Exactly. And this leads us to a profound insight. If a particle's position is perfectly known, its momentum is completely uncertain, and vice versa. This is the essence of Heisenberg's uncertainty principle, which states that we can't simultaneously know both the position and momentum of a particle with perfect accuracy.
So the more we know about one, the less we know about the other. That's a fascinating concept. It seems like the delta function keeps popping up everywhere in quantum mechanics, helping us to understand these fundamental principles.
It's a versatile tool that helps us grasp some of the most counterintuitive aspects of the quantum world. It's a reminder that even the seemingly simplest concepts can hold incredible depth and reveal profound truths about the universe.
It's incredible to think about how this seemingly simple concept, this spike we call the delta function, can have such profound implications in physics and mathematics.
It really showcases the elegance and power of mathematical tools in helping us decipher the workings of the universe.
We've explored so much today, from its unique properties and how it helps us understand instantaneous events to its role in signal processing, quantum mechanics, and even the uncertainty principle.
And we've seen how it helps us model not just these instantaneous bursts of energy, but also continuous phenomena like the behavior of an electron trapped in a potential well.
I'm starting to see how the delta function acts as a bridge between the abstract world of mathematics and the very real phenomena we observe in the physical world.
It's a powerful abstraction that helps us simplify complex problems and gain insights that would be much harder to obtain otherwise.
But before we wrap up, I'm curious. Are there any limitations to the delta function? Is it like a perfect representation of reality, or are there aspects of the real world that it can't quite capture?
That's a great question, and you've hit on a crucial point. The delta function, while incredibly useful, is an idealization.
So it's a theoretical tool that helps us approximate reality, but doesn't necessarily reflect the nuances of the real world.
Exactly. In reality, no event is truly instantaneous. There's always some finite duration, however small.
That makes sense. So where do we go from here? If the delta function is this idealized tool, what other mathematical tools are out there that can help us model the world around us with even greater accuracy and depth?
Oh, there's a whole universe of mathematical wonders waiting to be explored. From differential equations and vector calculus to probability theory and even chaos theory, there are countless tools that help us understand and predict the behavior of systems, both simple and complex.
It sounds like the journey of mathematical discovery never really ends.
Absolutely. There's always more to learn, more connections to make, more mysteries to unravel. The world is full of patterns and relationships waiting to be discovered.
This has been a fascinating journey. I feel like I've gained a whole new appreciation for the power of mathematics and how it illuminates our understanding of the universe.
It's been a pleasure sharing these insights with you. Remember, curiosity and a willingness to embrace the beauty of mathematics can unlock a world of understanding.
Thank you for listening to Podcast Learn and Fun. If you like our videos, please subscribe, click the like button, comment, and share. See you next time.